We should have had that review on tape, but we start now with the recording. And rule number 5, the product rule. Yay! So, if adding and subtracting just said find the derivative of them separately, the first thing that Leibniz thought too is, well, what if we're multiplying two things? Can we just find the derivative of them separately and multiply? Because that would make life really easy. So that would be a first logical guess. And unfortunately, that first logical guess was wrong. It didn't work. And you can see why if you take something simple like one function's x, the other one is x to the 4. It's really easy to see if you multiply those two together, you would get x to the 5. And the derivative of x to the 5 is just 5x to the 4. That's like super easy for us. But if you did the derivative of them separately, the derivative of x would just be 1, and the derivative of g of x, or 4 of x to the 4, would be 4x cubed. And if you multiplied them together, it wouldn't work out. So then I have to go back and say, is there actually a rule that would help us find things out when we're multiplying? Or is this something we always have to go back to our definition of a derivative? So does it make sense that it doesn't work in this situation? Like, it's obvious that if you had these two functions multiplied together, that's obviously equal to x to the 5, and its derivative would be 5x to the 4. But if you did the derivative of each of them separately, this one's derivative is 1, this one's derivative is 4x cubed, it does not equal the actual derivative of 5x to the 4. So back to trying to figure out if there's any pattern that exists. And the mathematicians did find them. And they're wonderfully complicated. So here's our first derivative rule that looks nothing like what you started with. If you have two things multiplied together and you want to find the derivative, what you do is you keep one of them the same. I kept f of x the same and multiplied by the derivative of the other one. Then you keep the other one the same and multiply by the derivative of the first one and add those together. It works, but it doesn't look, it's not a simple thing where you're like, oh, this makes total sense that this is what you would do. So we have it in notation of Newton, and we also have it in the notation of Leibniz. So if y is two functions u times v, then the derivative says keep one the same and multiply by the derivative of the other one. Then keep the other one the same and multiply by the derivative of the first one. So you're always keeping one the same and multiplying by the derivative of the other one. Can you see that because you're adding, it doesn't matter which one you keep the same first? Keep one the same, multiply the derivative of the other one, and then add. Keep the other one the same, multiply by the derivative. So that's what I'm basically saying here. Keep one the same times the derivative of the second. Keep the other one the same times the derivative of the first. Okay, so let's get to some examples. In this example, you have choice. You could do this one using your old rules, but you'd have to simplify first. Or you could do it using your new rules, and then maybe have to simplify afterwards. So I'm going to split this up. In the old way, I would first multiply this up. Can you see that you could distribute and get 2x cubed minus x squared? If you had 2x cubed minus x squared, now you're just adding and subtracting, so you're allowed to find the derivative by bringing the exponent out in front, subtract 1, bring the exponent out in front, subtract 1. The old way in this case, I think, is quite nice. Nothing crazy mathematical. Okay? The new way would say you can find the derivative if there are two things multiplied together. I'm going to put a dot there, and I'm going to put a yellow box around this one and an orange box around this one, just so we can see that we have the yellow box times by the orange box. It's important to be able to see where the multiplication is. So the derivative rule says keep one the same. So if I keep the x squared the same, and then I multiply by the derivative of the other one, can you see that the derivative of the orange one would be 2 plus 0? Because you could do the derivative of 2x, that would give you 2, plus the derivative of minus 1 would just be 0, would just be 2. Then we go plus, keep the other one the same, so now I keep the orange box the same, and the derivative of the first one would be 2x. So I'm going to underline in orange here when I did the derivative of the orange one, and I'm going to underline in yellow here when I did the derivative of the yellow one. And this is the yellow box that stayed the same, and this is the orange box when it stayed the same. So this idea of keep one the same and multiply by the derivative of the other one, then keep the other one the same and multiply by the derivative of the first one. Now if I simplify this, I would get 2x squared, distribute here, plus 4x squared minus 2x. They simplify to exactly the same thing. So now you have choice. Simplify first, then do the derivative, or derivative first and simplify afterwards. Here's a new notation for you. This d dx means find the derivative of what's in the brackets. So I'll try to introduce as many notations that mean the same thing as possible. In this case, if it's really easy to multiply out, which I think this is, can you see that that was really easy to do? To distribute that x cubed? I would do it that way. I would use our old techniques. Even though this is in the product rule one, where we could keep one the same derivative of the other one, this seems easy to do. And the nice thing is your final answer is already in simplified form. But there's going to be situations like, ooh, I don't know if I want to FOIL it out and combine all the like terms. This is like an in-between one. It wouldn't be hard to multiply this out. I don't want to. And so, if we, again, notice where the multiplication is, I'm going to put a yellow box. There's my first function multiplied by my second function. And my derivative would be, keep one of them the same, multiplied by the derivative of the second one. The derivative of the second one is 6x minus 1. Then keep the second one the same, 3x squared minus x, and multiply by the derivative of the first one, which would be, bringing 3 out in front, 6, subtract 1 from the exponent, plus 0, which is just 6x squared. And what's actually really nice in a lot of calculus questions, they're like, don't worry, you don't have to simplify. You want to leave your answer like this? It's fine. So you're like, nice. Because after I multiplied it out, I'm like, oh, I would still have to FOIL. So maybe I should have FOILed right from the beginning if I wanted to simplify it. That might have been nice. I'm going to color code again. Can you see this is where I kept the yellow one the same? And this is where I have the derivative of the yellow. And this is where I kept the orange one the same. And this is where I have the derivative of the orange one. And this is also where, when you're doing calculus, when somebody doesn't know the special rule, it looks like magic. It's like, where'd the 6 come from? Someone would look at this, they're like, I don't get it. And then you just smile and you're like, you're not supposed to get it. This is calculus. This is like a secret society. We know the rules and you're not allowed to learn. So how do you recognize when you should use the product rule? Well, you're just looking for when do I have two functions multiplied by each other, where I know the derivatives I could do of each one separately. So in this case, I'm like, okay, we're multiplying right here. So this is my first function, and this is my second function. Inside of both of those, could I do the derivative? Could I do the derivative of the yellow one? Could I do the derivative of the orange one? The answer is yes. Then you're like, okay, I can follow these rules. I can find the derivative. Well, orange. F prime of x, I keep one of them the same. Multiply by the derivative of the other one. Then keep the other one the same. Multiply by the derivative. So color coding again. This, I kept this one the same here. I have its derivative there. The orange one was kept the same there. And its derivative is there. So we do really need to have those derivatives memorized, because I know they're on your formula sheet. But taking the, I don't know, how long would it take you to memorize that natural log of x is 1 over x? How long does that actually take? Right? And if you're remembering something, okay, when you're doing this question, you can also go, how long does it take when I'm doing a question to pull out my formula booklet, look it up, find it, then write it down? Okay? If you're working on your derivatives, you can actually memorize them at times where you're not doing anything else. Right? I don't know, how many of you are on a bus to school? Or how many of you walk to school? Or how many are you are in a car with somebody, with a parent, sibling, relative on the way to school? You're probably doing one of those things. While you're walking, if you just sort of like, okay, I'm just going to go through my head, do I know the derivatives of all the major things so far? You are memorizing them at a time when you're not doing anything else really important. Right? And that's going to, when you're doing your homework or doing the quiz and you have to look it up in your formula sheet and it's wasting your time, you're feeling at that moment it's wasting your time. Take time in other places, think about this, to see if you can remember the derivatives, because it will help you so much, saving you time in the future in these units. And again, we can leave it like that. Do not simplify your answer. Very nice. Okay, 30-second head start. Try this one. Try this one on your own. And then I'll put up the answer. And then you can try the next one on your own. How many of these ones can you do on your own? Oh yeah, and number 5. Number 5 asks you to simplify. All right, how did you do? Okay, try the next one. Now, you could have written, plus negative sine theta if you wanted to for the derivative. I just put that plus and minus together as a subtract. Good. So again, this idea of, right, if you have the rule in your head, keep one the same, derivative of the other. Here's keep one the same, derivative of the other one. Then keep the other one the same, derivative of the first one. Also, not very hard to remember the product rule with words like that. And again, that's going to help you out. We're gonna have fun with the product rule. I'm gonna make up one after we're done the product rule questions here. Look at the next one. So it does say simplify. So because it says simplify, I'm kind of like thinking, would it be better to do product rule first, then simplify? Or would it be better to simplify first, then do the product rule? I mean, then just do regular derivative rules. So either way. But because it's in the product rule section, I started off with product rule first, simplify after. And then you can multiply it out, distribute everything, put together your like terms. And our last example here. Let g of x equal 2x sine x. So we could think of the multiplication as between the 2x and the sine x, or you could think about multiplication between the 2 and the x. There's more than one multiplication here. So what you really have to determine is where I put, or I don't have to do this, but like where I decide to put these two boxes of the two things multiplied together, I have to make sure that I can do the derivative of each one on its own. And if it's this way, I know the derivative of 2x is just 2. I know the derivative of sine is just cos. So I'll be able to use my product rule. Keep one the same, derivative of the other. Keep the other one the same. And once we start getting into more and more rules for derivatives, your brain starts to forget what is a derivative really. And again, all a derivative is the slope, is an equation to find the slope of a tangent at a certain point. So 2x sine x, that's actually a pretty crazy looking graph. It's actually kind of cool. Oh, wow. It's like a sine graph that's getting bigger and bigger and bigger and bigger as you go along. And this happens to be the formula for every single tangent line. So if you wanted to find the gradient, and the IB likes to use gradient as a fancy word for slope. At x equals pi, all you would have to do is find your derivative at pi. And what does this mean as far as what you need to know from last year? Oh, what do you need to know? Your pi plate, your unit circle. Do you remember what cos of pi is? Sine of pi? Cos of pi happens to be -1. Sine of pi happens to be 0. So we get a slope of -2 pi. Now I want to skip the next example. I'll show it in the video here. So, oh, was everybody done? Everybody good? Yes? Okay. So the next example, I'm not going to get you to write it down. We'll just explain it quickly. You've got a function. Find the gradient of the normal at the curve. So you would have to find your derivative. That would find all of your slopes of your tangents. So if you plug in pi, you would find out that you get the slope of your tangent to be -e to the pi. Then if you wanted to find the slope of your normal, right, it's perpendicular, so you just do the reciprocal, flip it, change the sign, and that would be the slope of your normal. But I wanted to have a little fun. So I'm going to give you a function. Oops, let's add a new page. Let's say we have a product rule if you're multiplying two things. What would you do if you're multiplying three things? So what if I had sine of x times cos of x times natural log of x? How would I do the derivative of this? Okay? Well, your product rule works if you're multiplying two things. Okay? So let's say we decided to use this as one and this as the second one. Okay? Then within the first one, you have a product as well. I'm going to use dotted lines. In the first one, I have this one times this one. Now we're going to talk through the derivative and see if it makes sense. The product rule says if you're multiplying two things, keep one the same, multiply by the derivative of the second, then keep the second one the same, multiply by the derivative of the first one. So if I start with that idea, back to green. If I keep the yellow one the same, you see that I would just have sine x cos x. Multiplied by the derivative of the orange one would be 1 over x. Plus, keep the second one the same, natural log of x, multiplied by the derivative of the first one. And now we run into what's inside the first one? Another product rule. So if I want to do the derivative of the first one, I have to go back into product rule mode. And for the derivative of the first one, I would say keep one the same, derivative of the other one, keep the other one the same, derivative of first one. And this would actually be the derivative of the whole thing. So now I'm going to color code it so that you can see what's happening. Can you see we kept the yellow box the same here, and then did the derivative of the orange box? Then we kept the orange box the same. And then here is the derivative of the yellow box. But in the yellow box, you have a product rule, which meant that you kept this one the same and did the derivative of this one, then kept this one the same and did the derivative of that. And this is the right answer for more than one multiplication. But we've kept the rule the same, just within the rule, we hit the rule again. Does that make sense? Like, while I kept this one the same, multiplied by the derivative of this one, then I kept this one the same, and then when I needed to do the derivative of the yellow one, it was like another product rule. So I just had to do it again. And you could expand this to do like 4 things multiplied. And you would have a very long answer. And all you're doing is the same rule again. But if someone saw you do this in one step, they would be like, and they didn't know calculus, it looks really impressive, really complicated, when it's a simple rule that you're just doing again and again and again. Okay? That is our problem.